Hi. We're going to talk about the material from lecture 4. Right? As usual, I want to say that watching these videos is not a substitute for reading the book or notes. You still need to do that. Okay, first thing I want to talk about is cumulative frequency. Right? And I won't write out the definition. It's in the book, it's in the notes. Essentially, you'll see what it is when I do an example. It's very simple. At each row of a frequency distribution table, the cumulative frequency is just the sum of all the frequencies up to and including that row. That's all it really is. Again, you'll see an example in a moment. Once we have a cumulative frequency table, where we have all the cumulative frequencies for the rows, we can make a cumulative frequency graph. Right? The cumulative frequency graph, that is going to be, first of all, a plot of some points x, y, right, where x is the right-hand endpoint of an interval in the table. Right? This is going to be a frequency distribution, only it's going to have cumulative frequencies in it. And y is the cumulative frequency at that interval. That's all it is. And then after you get done plotting the points, you'll join adjacent points with line segments. It's very, very easy. Okay, let's do an example. You can see here I'm given a frequency table, classes and frequencies. There's 1 point in this class and 1 point in this class and so on. I'm supposed to add a column for the cumulative frequencies, and then I'm going to go ahead and make a cumulative frequency graph. Okay, so when I go to compute the cumulative frequency of the first row, that's just the sum of all the frequencies up through and including the first row. So it's just going to be 1. When we get down, I think of moving down through the table row by row and adding up the frequencies I've seen so far. Right? So at the end of the first row, I've only seen 1. Right? At the end of the second row, I've seen this and this, so that's 2. Notice that I could have gotten that same number by starting with the frequency, the cumulative frequency in the first row, and then adding the frequency from the second row. Similarly, for the third row, I could start with the cumulative frequency from the second row, add the frequency from the third row, and get that. 2 plus 1 is 3. And then I would add 10 for the next row to get 13, and then 23, 25, 29. And you can see here that the sum of the frequencies, I've already figured it out, is 29, and the cumulative frequency of the last row had better be the same number, right? Because the last row should be the sum of all the frequencies. Okay, now I want to make a cumulative frequency graph. First, I'll do that in a second, but first, what are those points going to look like on the graph? Right? What are the x, y's? Well, in each row, the x is the right-hand endpoint for the interval. Right? So 25. So this is going to be for the first row, 25, comma, and then the y coordinate is the cumulative frequency for that row. So 25, 1. This one would be 29, 2, 33, 3, and so on. Okay. Let's draw the graph. So there we go. We'll just do this. I'm going to need the right endpoints here. So let's start with 25, 29, 33, 37, 41, 45, 49. Okay, and then I'm going to need to put the y values, the cumulative frequencies here, and those are going to go up to 29. So let's see, I'm going to put 30 right there, which will make that 20, 10, and so on. Okay, so the first point would be 25, comma 1, which would be something down here. The next one would be 29, comma 2, and the one a little higher. Then 33, comma 3, and then 37, comma, right, 37, comma 13. 37, 13 would be about there maybe. And then 41, comma 23. Let's see, maybe there. 45, comma 25. And 49, comma 29. So once I have those dots, I just join them with little line segments. Et voila, there is my cumulative frequency graph. Okay. Okay, the rest of this brief lecture is about other pictures of data. Right? Mostly you've seen these before. I'm going to say a few words about them, very little. Right? Pie charts, right? The first one, mostly used for showing categorical data and something about it, the count or the frequency or the relative frequency, I mean. Right here, this happens to be the income of the U.S. federal government by income category for one particular year. So like this sector here corresponds to Social Security. It looks like 34% was of the government's income that year was from Social Security taxes. This represents individual income tax, and so on and so forth. Right, here's the corporate income tax for 11% and so on. This is just the outlays for the same year. Pie charts, very simple. Another very simple thing is bar graphs, right? Often called bar charts. You can see them here. You'll notice that the bars are separated in bar charts, whereas they are not separated in histograms. Again, not exactly a make or break difference, but it's a useful difference. And once you get used to looking at both, you realize what each one is without thinking about it. Along one axis, you usually have classes. Bar graphs are also good for quantitative data, so you might have other numbers here and so on. And along here, you'll have usually either the frequency or the relative frequency. Right? So in this case, we have color versus number sold. I don't know, maybe this is color of cars sold in 1 week at some dealership, and they sold 5 red cars and 3 white cars and so on. Right? And this is just exactly the same picture, only the bars are horizontal, right? And of course the labels are reversed on the axes as well. Okay, a Pareto chart, as it's called, is just a bar chart for categorical data in which the categories are ordered from highest to lowest frequency as you go from left to right. This is useful. This is widely used in social science presentations because it allows you to see what the most important categories are all grouped together. Right? If you have many more categories, then it's much more useful. You just get to see where the bulk of the data is right away when you do that. Okay. Line graphs, well, we've already made one, right? The cumulative frequency graph is a line graph. They are for bivariate data, that is for ordered pairs only. All you do is plot each ordered pair as a point, right, on a regular Cartesian plane, and then you join the dots with line segments. Again, something you've been seeing your whole life. You don't have to label them the way they are here, of course. Just want to say a word about time series charts. There's some time series charts are just line graphs, but they've got a special thing about them. Right? The points on the x-axis here are regularly spaced times, like January, February, March, April, and so on. Right? These are 1 month apart. That usually a time series represents the measurement of some quantity. Here we have 2 different quantities plotted together. The measurement of some quantity at regularly spaced times. In the real world, you can have irregularly spaced times because sometimes, if you're measuring the amount of rain each day and you're plotting the amount of rain each day and your rain meter gets knocked over one day, that's going to be missing. So the times in the real world may not be actually perfect, but as much as possible you would like them to be regularly spaced. And in this class, if we use these, they always will be. Right? Here you can see this. One of these represents the number of visits to a website, and the other represents the revenue during that same month. And you can see they kind of either both fall or both rise together. Scatter plots, you've seen these, but you may not be so familiar with them. They are also for bivariate and numerical data, quantitative data, that is to say, ordered pairs of numbers. All you do is just graph the ordered pairs. Put a dot where each ordered pair shows up, right, at the point that each ordered pair represents. There's nothing to making them, but they are extremely useful. In fact, they are what every statistician or data scientist begins with when trying to understand data. Right? Plot the points and see if you can see any patterns. It's very important. It sounds like nothing, but it's very important. Here are a couple of pictures. I just want to point out a few features that'll come up later in the course. This particular scatter plot has the populations of various counties along the x-axis, and the solid waste generated. That's how many tons of stuff ends up in a landfill for each of those counties. And you can see the points fall pretty close to a straight line there. Not exactly, but pretty close. Right? And that's something you would expect. You would expect that each person generates, at least approximately the same amount of solid waste as any other person. Right? Not exactly, but pretty close. So you would expect that each time you added a person, right, you would see about the same amount of increase in the amount of solid waste generated. And that's exactly what happens here. This correlation is called strong because these dots fall very close to a straight line in this case. And it's called positive because they go up from left to right. Okay, this is a strong positive correlation. This is not obviously not on a straight line, although not far from one, to tell you the truth, but it's not on a straight line, it's on some much steeper curve. Or at least it begins to get steeper near the end. All this is along the bottom we have calendar years, and here we have the snout position of a glacier somewhere in the northwest U.S. I don't remember exactly where, Montana or somewhere. Right? And the snout position is simply the southernmost point. Right? So you go in and let's say in 1985, and let's say this is the shape of the glacier, and you drive a stake at its southernmost point. And the next year you come back and you find the glacier is here, and its southernmost point is here, and so you drive a stake in there, and you can measure the distance. And if you do this over a series of years, you can see how the glacier is retreating, that is, melting. Right? And this was the result for one particular glacier. This kind of correlation is also strong. These fall perhaps not near a straight line, but near some curve. Right? And they're not dots just all over the place. And it's negative because the dots are going down from left to right. Negative correlation. If you put the best possible straight line through those points, I don't know, I just made that one up, but it would look something like that, and it would have a negative slope. Right? Here's a third example. This one shows ticket prices in some season, back 1889 to 90. Ticket prices for NBA games versus how many people were in attendance. Right? And you would expect that if you set the ticket price down to 0, you would get an awful lot of people attending. You'd get a dot way up here, right? As full as the stadiums could get, probably. And then if you set the ticket price very high, let's say out to $1 million, well then, only Jack Nicholson would show up, and you'd get a dot way down near 0 here. You would expect this to decline as price went up. You would expect attendance to go down, so you would expect a negative correlation. Over the range of real prices, though, I don't know, what is this, 10 to about a little less than $30 that year? Over the range of real prices, there isn't that much negative correlation because, people are willing to pay a little more to go see a game if it's not too much more. So you only see a teeny bit of correlation here. It mostly just looks like a cloud of dots. All right. We will use scatter plots more in, as I said, in the late section of this course. They'll show up once again in an important way. That's about all I have to say for this lecture.